Ohio State. Zeyu has done a lot of really exciting work in pseudo-randomness, coding theory, and algebraic complexity. And today he's going to tell us about some recent work on combinatorial misdecoding of read-solved numbers. So Zeyu, go ahead.
Okay, thanks for the introduction. Yeah, so just finished the slides today. I didn't have much time to practice, so if anything is not clear, feel free to interrupt me. Okay, so this talk is about arithmetic codes, which are useful mathematical objects, both in theory and in communication, data storage, and so on. So the idea is that we want to commit some messages, but in our world, there's noise, right? So when we say message, you don't exactly get what you want to send. So to battle against noise, you want to encode the message into something such that you can start with X or X prime, they get encoded into code words, and these code words are far from each other, so that even if some error happens, you can still tell from the received word which code word they come from. To tell apart, because they are far from each other, you can still tell apart these code words. So let me first give you the definitions from basic notion. So we also talked about linear codes. So we have alphabet. For linear codes, alphabet is just a finite field at Q, a finite field size Q. We say linear code C the K linear code or Q. It means that it's simply a K-dimensional linear subspace of the vector space at Q to the n. And I have two important parameters. One is the code rate. For linear code, K linear code, the rate is just K over n. So this rate matters how redundant, how much redundant information you include in the code. We need to include some redundant information because we want to correct the errors. Right? So also the alphabet is the finite field of Q, and code distance is defined to be the mean distance between the code words. And here, distance between the two code words X and Y is defined to be the number of coordinates where X and Y equal. So this is called the Hamilton distance. The definitions, code rate and distance. If you want rate to be high, because we don't want to go too much redundant information, but at the same time, we want the distance to be large enough because we want to correct errors. So there's always tension between the two. So starting the trade-off is about the potential question. But today we're going to look at something different from the list decoding. But before that, let's first look at classical family of code called the reasonable code. So reasonable code is a code defined by evaluating low-degree polynomials at the points signified. So you can think of the message as a polynomial of degree less than d, so it has a less than k. So it has a constant degree up to degree k minus 1. So there are k coefficients. And you take such a low-degree polynomial, and there we fix n invariant parts alpha 1 to alpha n in Q. So that would force Q to be at least n, by the way. So the alphabet is that it has a size that is n, and then we take the low-degree polynomial, evaluate as alpha 1 to alpha n. Get n-dimensional vector. So this the image of this map doesn't have to evaluate the decoding map for this sort of code. And you can show that this is a NK linear code, and this distance is pretty good. Actually, the distance is exactly n minus k plus 1. The code that achieve this n minus k plus 1 are called the maximum distance separable codes, MDX codes, and so the reasonable code is an example of MDX code, which is optimal because there's a problem called similar dot, which is based on distance and most n minus k plus 1. So this is optimal. But I just said that so the way is that distance here is optimal given k. I just said on the side that we don't fully understand. This is a simple question that given the rate, you want to know what's the maximum distance. But here, we know reasonable code achieve the maximum distance. But this is only when reasonable code exists, which you require Q needs to be at least n. So the thing is that the alphabet size is smaller, like the local like 2, because the coding code. The threshold code don't exist, so in a setting where alphabet size is small, we still don't know what's the best possible distance given a rig. When Q is large enough, think about it's optimal and the result code achievement. Any questions?
Linear code.
Yes, it is.
Suppose there are no rules whatsoever.
Yeah, even no rules. I think there's also an MPS, singleton bound, but I'm not.
That is the lower bound. And would be better.
There is, well, I mean, this singleton bound is the upper bound of the distance. Yeah, I'm not exactly sure,
Okay.
but it should be something similar. Maybe it would be in terms of the size of the code and distance. Yeah. I think we quite similar to this. Maybe you can save a factor, small factors. Okay. So this is some called. So today, this talk is about this decoding, this decodability of resolving code. So I think so. First, explain what is this decoding. So the traditional notion of decoding is called a unique decoding. So we are given the transmit code, transmit message, transmit word, which is the correct version of the code word. It's called Y. Y can be different from X, and we want to find out X given Y. It turns out that if this is X and Y is a half of the middle distance, you can uniquely determine from Y. But if you just look at timing balls and at the Y radius, no more than half of the distance, the X will be unique. It will be a unique code word in this time point. Now this is good, but in some situations we want to know if we can recover X from Y, where the distance between X and Y is beyond half of the middle distance. Now in this case, it's not hard to show that it's, just basically we are looking at a larger radius, but then it's not hard to show that then the X will not be unique. So we have to give up uniqueness. This is a notion of this decoding, which is in 1950s. So it's about given the receipt or Y, efficiently find the list of X such that the distance between X and Y that's all equal to some row times n, where row is a small, row is a number between 0 and Y. So the idea is that we can give up the uniqueness, but we want this size to be small. Like but by allowing one-on-one code words, we can go much beyond the half of the distance. So one example is like spell checker. When you make a typo, the spell check will return the list of suggestions, but not more than one. So that's the example of the list coding. So this has
Just a quick question.
Sure.
If you don't mind, efficiently is it that random quotes is good?
Random, yeah, I'm going to say that the randoms these have probably very good so
Errors are strictly substitutions. Not
error, okay, you can do this very quickly. You can study not most common settings of substitution errors, but I think you can also study insertion deletion errors.
Yeah.
The stuff is not
You
long.
drop symbol.
Yeah, I think we can talk about that. Yeah. Paper, but I will work on that. But yeah. Right. Yeah. Yeah. In this talk, we just found the normal setting for substitution errors. Okay, also to motivate this definition, this is very useful notion, not just in coding theory, but also in method theory. People find this application about this coding. Let me just give you one application that is hardest was the randomness. So this is about say you can construct what we call a pseudo generator, stretch a short seed into a long string which still looks like random, as long as against those functions that are computationally bounded. As long as the function is not too powerful computationally, the output of the generator should look like random strings. Now this is not easy to construct unfunctionally, but this Harris-Randomness says if we know a function f is hard against certain class of functions. I can use that to build the this object. That without how the random speed would look like the random string. Now, but there are different ways to define to define what it means to say a string looks like a random string. One way is using this notion of predictor, so absence of the predictor. So we can consider the output to be random, pseudo-random if for any computationally bounded function p, given the first, so if p is given the first I bits, it cannot predict the next bit. So this we can probably that perhaps predict the next bit is at most slightly above 1/2. So this is the thing that we cannot do better than just make a random guess. So we just make random guess probably is 1/2. This we call it that we cannot do slightly better than 1/2. So this is one way to define the string be random against the combinatorial function. And the way we prove this is to do the counterposing. You say assume the output is not pseudo-random. That means there exists a p, originally bounded p that can predict the next bit. Then somehow that means you can learn, contributively learn the next bit. And then we can recover it from this predictor in some way. Which is kind of an analogy to decoding process. That actually, in fact, more than analogy. The standard proof of this uses decoding techniques. And to get the best parameters like this plus epsilon, we should use least decoding. So least decoding allows us to achieve this error of close to 1/2. Because if you use unique decoding, follows the kind of proof. The best kind of hope is like you can only say the predictor cannot predict.
Is epsilon go to 0 as?
Yeah, epsilon is sometimes not.
It goes to 0 as the string gets larger.
It's so actually I think it would depend on the you can always. I think. You can the thing is amplify this. You can make it arbitrarily small by
Yeah.
I think by
Making it.
changing the complexity parameters, I guess.
Yeah, you deal with.
Oh, okay. I think to reduce epsilon, if you want to regularly encoding, you can always change the parameters in the arbitrary code you use. I use a longer code. Yeah. But as I about to say, the proof works by arithmetic. Because if you can learn contributively, then you can decode the argument f. You assume f is hard. So that leads to a contradiction. That's how it's very true. Yeah.
This is just one word how does, but I mean, now that you're list decoding, you have multiple options to decode. No, because I mean, if it was unique decoding, but how to handle the list?
If you only use only unique code, you can go at most half of the mean distance. So if you carry out the proof, the distance is best can show.
No, that's true, but I mean, when you do list decoding, now you have multiple options.
Yeah, for list decoding, you can go very close to the whole mean distance.
But you have to pay for it because now
You have to pay for it because this is longer, but not big problem with it's still reasonably short. And the complexity can enumerate there's some way to hardware the device to tell which one the calculation comes from. Okay, it's just hardware short the device. It's really not hard. But it allows you to go all the way to close to the following distance. So that's how you can get it. Otherwise, you can get that, which is much less expensive. That's why this is a motivation application.
So for instance, what should be the size of the list? Should it be small of n of everything, or it should be like exponentially small and all possible?
Especially polynomial in no, yes. I think that's good enough. I mean, because of model like if you want to show, this one possible result as ratio. The half function against PPP against the sometimes in E, they can use it to be 1 max BPP. I think there, this such advanced phenomenon in S, but S is much more, and S is like polygon login. So we keep phenomenon login. Okay, so this is why into capacity series values. Very interesting topic. But today, but this requires not just we have a bound on this. We also need the algorithm to do the recovery. So there's important that we have to do the algorithm. But today we want to look at the easier path, which is it's called combinatorial, which means we don't care about the algorithm outputting the list. Potential code words. We just want to bound the number of code words, the size of the list. Now this is a necessary condition to get the efficient. Like if the number of code words is extremely large, but obviously to output the whole list, they have to first get a bound on the list. So this is the combinatorial list definitive. Now, so formally, given the number row and L, serial code is row L is code going for every y is the received word. There are no more than L code words that is within the Hamming distance of Hamming distance radius row times z. That's what it says that if you look at L plus 1 distinct code words, at least one of them is outside the code word and the Hamming distance. So the maximum of the distance is one scale multiple times. So this is that here. But if you look at L plus 1 code word, at least one of them is outside the Hamming distance. In other words, say any Hamming distance radius row times this at most L code words. Now there's a stronger version which if you look at L plus 1 is code words, not only the maximum is greater than 2 times the average is also greater than. This is called the average units. Okay. So I just talk about the resolvent code, and its distance is n minus k plus 1. So which means we have to unique decoding. We can do up to half of in distance. So it's half of n minus k plus 1. But for this decoding, what is its limit? Right? What is the best can do? Now there's let's go back to Johnson bound, which says any linear code with distance t is this decodable up to this radius, 1 minus square root 1 minus d of c over n, this small size L, small size. As a corollary, if you plug in the distance n minus k plus 1 for resolvent code, you see we said that you can this decode up to the radius 1 minus square root of r. This is the relative radius. If you have done the absolute radius multiplied by n. So this is the radius from Johnson bound. So any code with large distance, the Johnson bound gives you a lower about how much for the radius. If you have the resolvent code, you get 1 minus square root of r. So there's Sudan, just to mention this very influential result, and they give an algorithm to efficiently. Yeah. So, but can we? The one very important, interesting question is, can we go beyond Johnson? We got the resolvent code. Okay. And what's the best I hope? So this is first of all under the question that what's the best I hope. So using the probabilistic method, we now show that the random codes, random code is actually high probability. This decodable combinatorially is decodable up to radius 1 minus r minus s. Note that similar about this 1 minus r. So this is okay. So this is 1 minus r minus epsilon, but other of these small radius, this size. But on the other hand, if you go slightly beyond 1 minus r, then the least size has to be exponential. So the 1 minus size is down the threshold. I'll mention that here, this is assume the field size Q is large enough, like at least n. At least I think it's only 1 over epsilon, like 2 to the 1 over epsilon. Like if you consider Boolean code, for example, I have 2. If this is not right now, so I'm just implicitly assuming that this Q is kind of large. The correct for smaller field size, there's also the least coding capacity, but the parameter is not R, it's in terms of culinary entropy function. But when Q is large enough, the culinary entropy function of X is approximately X. So I can do this simplification, but the Q is small F2, you have to use the entropy function.
But it's still random chords that shift, you know.
Yeah, I think so, yeah.
Are either of these linear?
The first one is now the, although I think there may be linear where it will be more, maybe I'm not probably measure it smaller. I don't think it's
So the lower bound is for all.
the lower one.
None of them.
Yeah. So when we say code is passive achieving, okay, this is over large field. This set this decoding achieve this capacity, it achieves the radius 1 minus R minus epsilon. It's reasonably small tab, which like even poly n q is good enough. So we said, yeah, and it's not easy to construct explicit capacity achieving codes. The first such code is called family of folding resolve, which is a variable resolve. Let's say we combine there's a parameter s, and we just combine s symbols into one symbol. Acrobat becomes equivalent. Three string is not linear. Yeah, so this is constructed by Goswami Rudra, so fine. But this is about folder resolve. It's not about resolve itself. So class the resolve code itself, because it's very simple, it's classical. So one know the resolve code the sheet is fantastic. There are some negative results that this may be too much to hope for. Challenge bar show that this is about efficient. This is a tool that if you can efficiently go to resolve codes up to beyond the Johnson bound, when beyond Johnson bound, then you can actually solve it's pretty long. So algorithmically hard. And even for combinatorial decodability, but that's the probability that hard. You should for that you consider full resolve codes. This, so all the parts are chosen as the other part. The model maybe you can relax this a bit by letting the end to be close to you. If you can do this, and this that it's not possible, not combinatorially decodable beyond Johnson bound to choose other parts. I think it will require the final field to have some extension field structure. We don't know how to do it. Put this in practice, yeah, this is a technical issue. So, but physics has maybe too much to hope for. To hope for beating the Johnson bound, even achieving capacity. But because you ask, for example, if you pick the divided points alpha ones then randomly from the finite field. Get a random resolve code, as a random code beats Johnson bound.
In the previous one, there is a fixed choice of alpha one.
Right, this says the choose
Oh,
all them. Maybe you can choose both some kind of background will still be. But yeah, when it comes to random resolve code, this is not easy question. If you just try promising method, the problem is that the resolve codes are very structured. Even if you choose the random path, still there's a strong structure. So if you apply promising method, it doesn't give you anything, at least in a straightforward way. So this is a question that you studied. There's some earlier work by Mary Wooters and actually Rudra. They put some setting, high noise setting. You can indeed beat the Johnson bound, but still it's far from capacity. The recent years, there's a very beautiful line for. So this is going to talk about in this talk. So the physics settled. I mean, it's not our work. This paper is physics settled this question. Affirmative. Okay. So this number start is a paper by Shangguan Tao. This was the full upper bound called the generalized signal bound. It says for any vehicle C with R, if C is the low L is decodable, it will be greater than L. Then there's an upper bound. There's two upper bound on rho, the radius, the relative radius. It says they show that the rho is at most L plus 1 times 1 minus. This is called generalized signal bound because which is L to be one, that's corresponds to unique decoding, then you get 1/2 here. If you think about the resolving code, 1 minus R is basically distance D for resolving code, for MPS. This is half of D. So this term tells you not go beyond half of the distance, which is what you already know. And so this is a generalization of that general value that have for any L, we can have this other one. If you choose L to be the conjecture is time, either achieved by this young result. But if we choose L to be of order theta or epsilon, this L over L plus 1 is like 1 minus epsilon. So what you get is that rho is close to the most 1 minus R minus epsilon, which is close to the actual one we see before. So my point is that this can be seen as the refinement of the capacity. But it holds for any constant L. If I talk about L equals 3, for example, this will give you 2/3 of 1 minus R. The conjecture this is tight, is even achieved by resolving code, which is pretty strong conjecture, and they prove that it's true. Conjecture is true for L equals 2 and 3, but you could not do it for larger L. How you about this proof of approach work? So this is a proof of strategy. So we want to basically say if random ROS in random forms, this hyperability that does not exist of one distinct with C0 through CL. Now assume to the contrary that's how they deal in this Hamming form. Assume to the contrary that they exist, right? As each CI comes from message, for resolving code, the message is a low degree phenomenon. We define this, assume it exists, so you have a prediction. So I define I subscript I to be the set of coordinates where the S code word CI, the grid is my received word. Okay, so I set I comes the pattern of agreement, set coordinate where CI grid is received Y. I also define Fij to be Fi minus Fj. So this Fij are parallel differences between the messages. The idea is to find the linear constraints on the Fij of coefficients of coordinates of Fij. Coefficients, Fij are polynomials. So we can look at coefficients. Think of this coefficients as variables. We're going to find linear constraints that these variables have to satisfy. First of all, Fij plus Fj must be Fk. These are definitions of Fij equals Fi minus J. So it's like a cycle relation. There's one type of linear constraint. Another relation comes from the agreement. So when if you think about this, for every coordinate R in I subscript I, Ci R, the S coordinate of Ci agrees with the S coordinate, R coordinate of Y. But if R also lives in Ij, the Cj of R also agrees with Y. So I'm saying, if you look at coordinates of R, index R lives in both Ci and Ij, Ci and the Y agree on R coordinate. Cj and the Y also agree on it. So therefore, Ci and Cj both agree with each other. And then that means the message in Ci, what is Ci? Ci is Fij. No, Ci is Fi value. Cj is J value. So they agree with their difference is 0, which means Fij value. Now, if you think about this, look at this equation. If you think about this equation is evaluating Fij at alpha is the value of time. So this is a linear function, even coefficient of sum. The value is the sum of the coefficient times the powers of the value of time. This linear coefficient of Fij, where very simple coefficient of Fij as variables. Coefficient are powers of the alpha. So you get the equation in the coefficient of Fij, you just put together all these linear coefficients. This all is the linear constraints. They form a matrix. And this matrix represents all the linear equations, representing equations, that actually is in a matrix, sorry, the matrix representing the linear equations, linear equations in the equations of Ij. This is what the China call the intersection matrix. The idea is that I want to show this matrix has a full column line under its hyperability and the random choice of the vector class. Because if you in full column line, then it has no non-zero solution, right? On the other hand, if Fij is for because this Fij is for codeword at this thing, you know, take the difference, the difference is non-zero. So it give you non-zero solution. But it's that because full column line will have no non-zero solution. That would be a contradiction. Yeah, that kind of question is that here like fixing it says I substitute I in the remain choice, but we can enumerate all the possible I substitute. And it's beautiful. Fix each possible I line. It is really great. But the idea is to try to pull out this matrix over random our choice of our is going to be have full line. Now, how do we show that random? It doesn't to show that when you view this alpha as a variable, symbolically, it has full rank. That will be enough. Because say the matrix is full rank, it's saying some minor as non-zero determinant, right? But if you can show this when alpha has variables, that is determined as a non-zero polynomial by Schwarz equal lemma, most of choice and polynomial. So, okay, so we just need to show the conclusion that we just need to show this matrix has symmetrically equal where alpha has variables. For some reason, because of assume certain conditions about its explain, but this is the conjecture in some paper. And here's the example of what the matrix looks like when L equals 3, upper half is the cycle formation, Fij plus Fjk equals Fjk. The lower part is the represents this kind of relations. So yeah, the conject this is a full rank matrix when alpha is computed variables. Now, they prove that this is true for L equals 2 and 3. Yeah, the ladder is more complicated. So in the follow-up paper, we look at what this determinant look at. So this is called my median Shangguan common rulers. We look at in general what this determinant looks like. We can calculate determinant of this matrix. So one can first of all we can build the we have agreement between codewords. We can try to use the build a graph. Then start with a hypergraph. But at each point have multiple can have multiple codewords agree on the one. They both agree to each other. So it starts with a hypergraph, but somehow we replace each hyperedge by the spanning tree, spanning that hyperedge. Now that is the graph. Once you have this graph, which we can call complete graph, then we show that this determinant can be written as the sum of monomials, which is plus minus 1 coefficients. Each monomial comes it's related from graph to the graph. So each monomial comes from what we call tree packing the graph. So tree packing is a collection of k, the tree packing of size k is a collection of spanning tree of the graph. They are such as they are h disjoint, don't share h's. Okay, the graph can have parallels. So you just just pack the k spanning tree, the k spanning tree into the.
Is it the standard dependent on tree packing? As in like Ti is the spanning forest of G minus T1 to Ti minus 1, or like the ith tree that you pick, is it like the greedy tree packing that the ith tree is the spanning forest, or your graph has like some k connectivity properties that they're all.
Oh yeah, we can't do this for general, but it doesn't have to be the tree packet does not exist. If it doesn't connect to, if it's not connected, it could not exist. Because
there won't be any tree packing.
possible, yeah. There's some condition is guaranteed. which I'm going to talk about. So basically here, for every tree pattern gives you monogamy. It's equal to plus minus one, and also, so this question is about, you can see, we need at least the existence at least one tree pattern for this to be possibly non-zero. Not true is non-zero, so we must at least show that there exists at least one tree pattern. Then there's this theorem, natural truth theorem, which is says if a certain if the process by a certain condition, the condition says if you consider partition of the vertices, such vertices into k parts, and look at the edge that cross the different sets, the number of such edges is always greater than or equal to k times the number of sets in the partition minus one. If this is true for any partition vertices, then it's guaranteed that there exists a tree pattern. Yeah, I should read more here, given that both Adrian and Tooth worked at this university and did amazing work. But yeah, this is so I'm talking about in our application, the condition of measuring Tooth theorem is satisfied somehow. So we apply this theorem, which gives us the existence of tree pattern. Unfortunately, just using this theorem is not enough, because in our setting, you can have two different tree patterns that give you the same monomial, which essentially is because they are considered hypergraphs. So you can have two different edges that come from the same hyper edge. They will be given the same. There's a labeling. They will give the same labeling. So they can have two different monomial that comes from same tree. Two different tree patterns give the same monomial, but maybe different properties of sun, so they could possibly cancel each other. We don't know how to rule out this. If this monomial is distinct, then we immediately that, probably immediately that it's not zero, but we couldn't prove it. So that's a main problem. We figure out some way, some trick to still get some non-pure results, basically by selecting a sum matrix and show that that sum matrix has full rank. But that trick leads to some loss, some logarithmic loss, which prevents us to prove that the original conjecture. So we couldn't. There's a follow-up paper by Berger. So in this result, we have a logarithmic loss. Berger one, Solomon, in a very beautiful short paper, they crashed our paper by including error parameters. So they also suffer loss, the constant loss in the roots. Yeah, it's not about this paper. This paper is a pretty nice paper written by Zeyu from Paris, which didn't really follow this framework, but for this one, we can really translate the result into this framework, and they can see what kind of, we use a very clever trick. That trick is very clever, but at the same time, they also look at constant. You look at that here, there's no hope to pull out the conjecture that is trick. So, the most important work in this lab the paper in this lab research is this beautiful paper by Rapidstack, and McCann. They just prove that the overlapping dot fields. They just prove the conjecture. And the way they prove it is we produce three notions of parallel methods. MDS means the distance is n minus k plus one. They're going to extend the notion, strengthen the notion to parallel MDS. So, in this paper, they propose three different notions of MDSL, GCPL, and LDMDSL. I don't have time to define all of them, but let me just mention that LDMDSL is what we are interested in. It says, basically it says the code is LDMDSL means it is achieve the optimal radius, the general in the box. In the strong sense of average radius. So this is if you prove this, that's good enough. If you prove that this one code is LDMDSL, and then it's good enough. So they prove that. So this notion comes from three different areas. So this comes from this decoding. Copy these are Microsoft, so they are interested in data storage, that kind of thing. This MPSL comes from data storage. So, and this GPPS comes from related different areas like network audience. So three notions that make sure that these three are equivalent to duality. More precisely, the code is MPS plus one, if I know if it's GCP plus one, if I know if the field code of C is LD and yes, L prime for all smaller, for L prime smaller than this inequality, which is really nice. And the next thing is that it's the GCP. It's already shown before, log it, so I log it and yield it, immediately yield this capacity that random reciprocals are probably GCP. So combine these two, and it also the fact that because here the equivalence is up to duality, so we need to find the duality, but it's known that the field of reciprocal is basically also reciprocal up to scale in the coordinates. So it's basically reciprocal. So combining all three proves the merit line. But I would say the more technical, other than equivalence, which is not easy to show, the technical input comes from this GM and DS theorem, which is very delicate to use a triple induction. I still couldn't really understand what's going on here. Although I follow proof. But it's not like I haven't fully understand. But if you think about there's one comment. We use natural theorem, right? I mean, and you can see back from the formula that for the determinant without zero, there must be at least one tree pattern. So you have to use natural theorem of some special case of it to prove the existence tree pattern. But this thing it doesn't make clear. My guess is that it basically doing the same thing, like maybe it's proving some stronger version of natural theorem. But unfortunately, it's not very clear. So I think maybe someone can develop the theory, clarify what's going on here. So yeah. So it's tight. I mean, the problem there is that we have natural theorem, but we need more. I need the phenomenon not cancel each other. That does not follow from the traditional graph theory statement.
You needed some like
yes, but yeah, also but into kind of algebra. Yeah, I don't know what it is, but maybe it already exists in literature. Maybe I have to do something new.
On the Python graph, is there a
Yeah, actually, there is. So there's a follow-up paper that shows give a quicker proof from GMMPS theorem to the main result, which use a paper, the work of Brown, what's his name? There's some work on hypergraph, K connectivity, that kind of thing. They use that to give a quicker proof from this theorem to the main result. But still, you need this theorem, so it's like you cannot get rid of them. I just don't really understand what the system is, but it feels like it's really similar kind of thing. Yeah. Okay. Yeah. So this is some comments. But this is not end of story. Because both Shaman Kamo and the practice their main result holds only with the field size is large enough. Now, if you look at how large is large enough, they require exponential field size. Now, the reason they need the exponential size is that this is due to the unit bundle where the other possible set system I substitute I has the set agreement, set coordinate where the code the wins the received word, probably numerous possible cases and take a look at. And that means that for each case, the probability of failure must be extremely small for us to conclude anything meaningful. It has, but on the other hand, the probability of failure is proportional to 1 over Q, Q is the field size. So that for this Q to be exponentially large. Now, but with mathematicians to jump, we come up with this very simple but also effective idea. So it allows us to reduce the field size. We will observe that we can actually reduce the probability of failure exponentially by just slightly relaxing the parameters. So let's suppose I don't want to exactly attend the general second bound. I can maybe reduce this rate by additive term, small term, epsilon. Then we show that if you just shooting for, if you allow epsilon here, you can reduce the field size from exponential to already. Well, the idea is pretty simple. If you our example to explain this idea, so I'm sure you can appreciate. So suppose we consider a example where we want to randomly choose a n by n matrix over a Q, where each entry is independently and uniformly chosen from a Q. We want this matrix to be full rank, right? But what's the property that is not full rank? It's if the calculation is hard to is linearly amount over Q, because basically that's because we're looking at the square matrix. Each time we pick a row has to increase the rank by 1. In particular, even if the first -1 rows are fixed and they're independent, in the last row to be not living in the hyperplane found by the previous one, and the probability that it does not happen is exactly 1 over Q. So you got 1 over Q, linearly 1 over Q as the error probability. But suppose I'm willing to relax the probability. So that will give you more linear constraints than the variables. So if you get a static rectangular matrix, you have more of those. And then think about if you choose the random matrix, M by N matrix, where M is 1 plus epsilon, and then what's the probability that is for rank N, odd rank. Now, yeah, something exponentially epsilon. Because you can, maybe each time you pick a row, you could fail to increase the rank. But it means
So
it's
it's not.
not very not full, that's close to not full. Yeah. You just think about it, even if you choose a bad row which fails to, which is fun than previous rows, you can just keep it, you can miss epsilon times, right? So the probability that it fails is found by something exponential, even if Q is small. But that's basically that. The actual application is slightly more sophisticated, but this is that. Yeah. So, and using this idea, we are able to put a field size Q to quadratic. Shortly after we post our paper, I guess our Robin was running the quickly put out post a paper that include the Q to linear. We put quadratic one to linear. And if this is finished, read our paper and figure out how to do it, and got a new paper in 2 weeks. Just give you an idea how competitive this area can be. Fortunately, it's after the deadline first, so we didn't have to compete against them. Although in the same paper, they also show that for linear, if you consider that linear, this proof this work not include the precise constant, even n. So we design shown now. So you may think of the problem for resolver code is difficult because it has a strong structure. But if for linear code, to get the it already has a linear structure. So for linear code, the linear code to get this structure, still with this structure. This is what the same thing applies to linear code, then yeah. And that's basically this line of sorry, this time for work. I just want to mention some subsequent work. You can be generated to other codes. Algebra geometry code is a generalization operation code where there exists distance is no longer for many years of algebra geometry code. The distance is not immensely plus one and not condensed, but they are very close to condensed code. Now the advantage is this more general family of algebra geometry code is that they exist even over small fields. You can make the field the reducible code Q has to be at least n, but there exists a algebra geometry code where Q is independent. So there is this extension where reference for Darm, Block, and Chow show that there exists certain families of random matrix code from certain families of matrix code where you pick the dimension cost randomly similar. You can get this radius, but the size field size is only given on L and epsilon, not n. So this is the direction for the code. Also, the Euro distance between code words is having distance. There's something called the rough distance, where the code words are matrices, and the rough distance between two matrices is defined to be the rough of their difference. I show that it's now defined distance is satisfied triangle inequality and so on. And this field has applications in the rough matrix code has applications in natural coding, and there's an analog result called calculated code. This is result that shows that calculated code achieve the same general signal bound. This is optimal, also optimal in relationship. Random variable achieve the general signal bound. And finally, there's what I mentioned is there's a I said the codewords is the first explicit family of code capacity achieving codes. So this is a codewords will have this form. You see each column represents a symbol, which is combined symbols horizontal into one big symbol. And this one, in order to achieve this capacity, and jump is solution, so they show that only the sum code list the average list total up to almost the general signal bound. So there's this pattern. S or S plus 1. S is the parameter, the correct combine S symbol together. That is the portfolio parameter. But if S is much larger than L, this thing will be very close to 1. So this radius will be very close to the general signal. So they show that if you can achieve this radius, which is close to the general signal bound for large S. But note that this is different from the previous result because this does not say anything about random sample, choosing the random paths. As long as this random paths are distinct, which is not hard guaranteed. And explicitly shows our bias that the random paths are distinct, this is guaranteed. So this is explicit code that achieve the general, and this is the first explicit code that achieve the general. And I think for the last work Thursday, we try to put the least type. This one is achieve the almost optimal trade-off because of the radius on this side. The unit type from the last work on this decodability and so on, but also something more. Most important difference is that if you replace the intersecting matrix by something different matrix but for the velocity. Yeah, I wish I have to explain this, but it's a very nice paper. I know a lot, several experts in this area get surprised by this result. I didn't even see this coming, so it's very nice. So finally, let me list some open problems. Directions. What we know is a random decimal code that she's like I'm setting out how many run has it. This is here, I don't see a approach of solving. I think this is a big open problem because let's say you want to know how to deterministically choose the non-roots of certain determinants. This is like polynomial testing, a big open problem. It's even harder because we have exponentially many determinants. For each set system, we have a corresponding second matrix. We want to find a common non-roots. Yeah, it's not clear how to do it. Second question is that everything, except the last one, last word, everything necessary, without counting these algorithms. You only have a combinatorial analysis that gives the bound on this side. Does not give any algorithm. So I want to design algorithm inside this. We don't know. Third question is just my curiosity. So can we make it more explicit connection with the tribes or the and so on? So finally, for this decoding, we now have a very good understanding of the optimal parameters. There's a generalization of this decodable code called the decodable, which other than factors U and L is an active parameter U and L. So we can define this decodable code. So for now, our understanding of the trade-offs is not known. So dependence on different is pretty bad. I mean, not very bad, but we don't know if it's an optimal trade-off. Although this work by turning out a lot of people now around parameters like that. I think here's a non-relevant school. Yeah. So that's everything. So thank you.